very weak connection here. I mean, the green edge is a weak connection. And so your cut could be something like this. This is your cut. So this is your S. And if you write phi for this S, which may not be the optimum, it is just like this. First of all, I should say that pi of S is the number of vertices, for example, inside S. Total number of vertices is 11, so it's less than half, so it's right with this condition. And phi of S is like, so these weights, such as 0.1, such as 0.3, such as 0.1, such as 0.4, these weights of graph are like transition probabilities. So these are transition from going from one to the another, transition from S to outside. So we call it escaping probabilities. If you divide by 3 over 11, it becomes 0.3. So it's like weights going out of the S over cardinality of S. And we love to normalize the weights of a graph to make it probabilistically valued. I mean, not ill-conditioned. It's well defined. So the lazy Markov chain, probability of x and x is greater than half. We use lazy Markov chain to avoid periodicity. I mean, what is the obstacle to mixing? I mean, first we should say that has the particle had enough time to escape from the starting point. And one bound for mixing time is half diameter of that graph. You know, we were talking about relation between the first eigenvalue and the diameter. Now we are talking about the same things. Mu minus phi by, let me just review it again. Mu of A minus nu of A over R A. And we define d of t to be maximum of pt x minus p. And we define t mixing time, epsilon mixing time, to be the minimum time that d of t is epsilon close. And we define d bar of t to be maximum of pt of x and 0 minus pt y. And we saw that by triangular inequality, this is sandwiched between d of t and 2 times d of t. And for example, if we have some graph like this, going somewhere from Z to A, let's say. And for example, D is the diameter of the graph. So, I mean, the maximum of distance between those A and Z for any A and T, for example. And epsilon is less than half. It says that the max epsilon mixing time, the mixing time is greater than d half. There is an interesting result by Varopoulos that is useful in improving many things, is that For a reversible, first of all, I should say what is a reversible. It means that pi of x, just to remind you, it is equivalent to this. And pi of x is always, degree of x divided by some normalizing constant. So this is what I mean by reversible. So it says that for reversible Markov chain, we can say that pt of a and y is less than equal to 2 times py pa e to the minus d2 a and y divided by 2t. And we can use it to prove many interesting things. Of course, this is the theory of in 1985. And what I'm interested to talk is about first I should talk about what is a cutoff. So by definition, a sequence of Markov chains, xt 1 2 3 4, this exhibits a cutoff if t mix of epsilon minus t mix, it is order of Tn mix for any epsilon between 1/4 and 0. And we also call a cutoff window if for x n t, if omega n is order of Tn mix. So it's like this. It means you're tracking the n of t in terms of time to see if it is close to this stationary distribution, and suddenly we see that it has something like this. So after some time, you will see that it drops. It drops from 1 minus epsilon to epsilon. And here is T mix. And T mix is, for example, for simple random walk on hypercube, it is n log n divided by 2. And Aldous proved in 83 that omega n is n. But heating time is also related to mixing time. Heating time, I was said, the heating time, the minimum time that it hits, that x of t goes inside A. And Oliveira in 2011 showed that for any irreducible reversible lazy Markov chain, T of mix is, so this is heating time related to mixing time. And heating time is the maximum expectation of TA, heating time. So now I want to talk about an important article. It has 94 citations. in 2008 by great minds like Ray Anderson and my favorite, Yuval Perez, the advisor of Cheyenne is Yuval Perez. So they work in Microsoft, and in 2008 they wrote a very interesting article. The title is Finding Sparse Cuts Locally Using Evolving Sets. Very beautiful article. So the conductance is the number of edges going from S to S bar, S complement, divided by volume of S, and we know volume of S is the sum of degrees in S. And so the input to this algorithm, let's call it let's call the algorithm local cut of V and phi, for example. So this algorithm had some inputs. Inputs is starting at vertex V, this vertex, starting at vertex V. And the target conductance that we are satisfied, that we say, okay, that's enough, search is enough, let me give me your partition, is phi. So the target conductance is phi, which is another variable. So it outputs. Output, it says after some time, after some calculation, give me a set S. That does work, I mean the time complexity of W. And the running time is important in Microsoft and in computer science, that the algorithm has work over volume ratio R of phi. If expectation of your work, which is a random variable, divided by volume of S, which is also a random variable, is upper bounded by that R of phi, is upper bounded by that work to volume ratio, R of phi, work to volume ratio. And the local cut outputs a set S, that phi of S is less than phi of with probability greater than half. So the algorithm has local approximation guarantee if for any A, phi of A is less than phi of A is less than phi, and the volume of A is less than 2/3 volume of G, and there is a set of vertices A prime of volume at least volume of A half, such that for any for all V this satisfies. So the local cut satisfies this. So we have A, we have your vertex that you have started, and A prime is there. And the process that they define in their article is called evolving set process. Evolving set process. So it's just a sequence of sets. It grows, S0, S1, ST, it grows. So it's like this. This set, it always grows until you say, okay, stop. It satisfies our target. It's enough. And then your lazy random walk with transition kernel P, X, and Y, we define it as 1/2 degree of X if X and Y is an edge, if x is equal to y, this is 1/2. So ptxy is a t-step transition kernel. And the probability that a lazy random walk moves from x to s is by definition, something like this, is by definition 1/2 a number of edges from x to s, then divided by degree of x, plus 1/2 1x in s. An example could be like this. You have a set S. Let me give you this example. So you have a set S. Here you have vertex B. Here you have vertex A, but vertex A goes into S. Vertex C is inside S, so it goes out with 3 edges. Also other vertices. So an example, if you just plug in, you will notice that P of A and S is, with that formula that I gave you, is just 2/6, because just 2 edges are going inside S, plus 1/2, and because it is outside S, so it is 0, this becomes 1/6. Similarly, P of S, B is, where is B? This is B. B is outside, so 1/2 3/6, because 3 edges coming to S. And then plus, because it is outside, we multiply it by 0, so it becomes 1/4. Similarly for C, C and S, C is inside S, okay? So this time, this term is not 0, so this is non-zero, so this is 4/6. And degree of UI, we have assumed that degree is 6. And so that was so what is the algorithm? One more time, I should say the algorithm is like this. First, so x1 joins S. With what probability? For example, you have A here, you have S here, so for example, this goes to B. And in the first iteration, they are not separated. They are not. B is outside S in the first, but after in the next iteration, it gets this. So S grows. So it was SK. Now it becomes SK plus 1. So when I say S1, I mean all the vertices that the P of Y and S0, this probability, is greater than U. And U is just a uniform. You draw it from a uniform distribution, 0 and 1. So it's just a random threshold. So this is the probability that if it is greater than U, then okay, you join that. So S1 is like that. So by induction, it grows and grows. So note that if you look at all endpoints in SK that have one vertex outside of SK, we can say that at step t is equal to k, we create SK and add some points. At step t equal to k plus 1, if condition met, add them to SK plus 1. And you know that 0 and V are absorbing states of this Markov chain. absorbing states. After some times, S grows until it reaches V. Or it is extinct, and you have extinction. I mean, it becomes